In this online lecture, we're going to discuss carbocation stability. And what we're going to do is understand why carbocation stability follows this trend. And that is tertiaries are more stable than secondary, which are more stable than primary, which are more stable than methyl. We're also going to see, too, that hyperconjugation explains carbocation stability. So let me show you these principles here. For this carbocation right here, this is the carbon that bears the positive charge. That carbon happens to have 3 carbons directly bonded to him, these 3 right here. If that's the case, then you're considered a tertiary carbocation, which means if this is a carbocation right here, then this is the carbon that bears the positive charge in red, and since he has 2 carbons directly bonded to him, he is a secondary carbocation. And an example of a primary carbocation would be this structure right here. Notice the positively charged carbon right here has 1 green carbon directly bonded to him, making him primary. And the last type of carbocation we should know is this one right here. Notice this carbon doesn't have any carbons directly bonded, so what we call him simply is a methyl carbocation. And here is the trend that we need to put to memory. We're going to use this a lot in organic chemistry, and that is tertiary carbocations are the most stable, methyl are the least stable, and stability increases as you go from the methyl carbocation to the tertiary carbocation. And that is our trend. Now, let's first learn how to use this trend, and then we'll explain the trend. So here's a sample problem. It's asking you which intermediate, that is carbocation intermediate, is more stable. Well, what you do, of course, is focus on the carbon that's positively charged and ask yourself how many carbons are directly bonded to each one. Well, for the first one on the left here, he has this carbon right here, 1, 2, and 3 right here, making him a tertiary carbocation. For the intermediate on the right, he has 1 carbon here connected to him, and this carbon right here directly connected, making him a secondary carbocation. That means that the intermediate on the left is your more stable carbocation intermediate. So notice, very easy to apply here. However, it gets a little bit more complicated in examples like this. For instance, which is more stable out of these 2 intermediates? Well, notice if you use that rule of thumb here, here's the carbon in red, he has 2 carbons directly bonded, making him a secondary carbocation. For the molecule on the right, here's the red carbon here, he also has 2 green carbons directly bonded to him, so they're both secondary carbocation intermediates. However, the molecule on the right has a Br halogen and the molecule on the left doesn't. The question is, how does that Br affect that positive charge on that carbon? Well, remember, we learned in previous online lectures that since Br is more electronegative, he is going to pull electrons this way in this molecule. And he's going to move them through a sigma bond, which remember happens to be called an inductive withdrawing effect. Think about how this affects the positive charge. If you're pulling electrons away from a positive charge, that's going to make it even more positive. And that increase in charge is going to make this species less stable. Remember, neutrality is stability. Being charged makes you unstable. Anything that increases your charge makes you less stable. So therefore, the answer to this question is this. This is the intermediate that's more stable. So careful, it's good to know the general trend of carbocation stability, but you might have to use other principles to get to an answer. Now, let's understand why we get the trend that we get. Here is a typical carbocation. If you determined his hybridization, you would see that he is sp2 hybridized, which means, remember, he has 3 sp2 orbitals about him, 1 here, 1 right here, and 1 like this. And that also means he has an unhybridized p orbital, and that happens to be where the positive charge resides. Or in other words, the p orbital has no electrons in it, and that's why the positive charge sits in that orbital. We're going to see that this empty p orbital helps us understand stability, so let's just focus on him. And let's focus on the most unstable carbocation, which is the methyl carbocation. For this situation, what you need to understand is that this positive charge right here is localized to that carbon. This is what happens in a methyl carbocation. Now, what does that mean? Let me explain that. What we're going to see is that the fact that the positive charge is confined or localized to one area makes this thing less stable. And let me show you this by comparing our carbocation to a primary carbocation. Remember, that means there would be a carbon, at least one, directly connected to the carbocation. And let's move it over here and let's put the hydrogens that would be connected to the right carbon. So here it is, our primary carbocation, which we know is more stable than the methyl carbocation. If you were to determine the hybridization of the right carbon, you would get that he is sp3 hybridized, which, remember, that means he would have 4 sp3 orbitals about him, like this. Remember, these orbitals are overlapping with the s orbital of the hydrogens, and these orbitals are filled with electrons. But what I want you to focus on here is the fact that the empty p orbital would be parallel to one of the sp3 orbitals to the carbon on the right. And because of this, it means that they're able to make a connection to each other like this. And what that effectively does is help spread that positive charge or delocalize it so that the average positive charge would be right here between the two carbons. These orbitals connecting to each other is called hyperconjugation. The fact that these orbitals are able to hyperconjugate means, again, that that positive charge is not going to be localized. That's one way to think about it. But here's a better way, I think, to think about it. Remember, it's the sp3 orbital on the right that has electrons in it, and it's the p orbital on the left that's empty. That means once these two orbitals hyperconjugate, the electrons in the sp3 orbital can now move towards the empty p orbital. And spreading out electrons decreases the energy of the molecule because, remember, electrons want to repel each other. So the fact that these two orbitals can hyperconjugate means that it allows the electrons to spread away from each other. That is almost equivalent to saying that positive charge is also spread out as well. Notice we wouldn't get hyperconjugation with a methyl carbocation. There's simply no carbon next door that bears sp3 hybridized orbitals. And notice the many ways in this case that this molecule can hyperconjugate. It could hyperconjugate with this bond like we saw in the example. It could also hyperconjugate with this one or even this one. And think about it, it makes sense. The more chances to hyperconjugate, the more we have the ability to stabilize the carbocation next door. So let's take this concept a little farther now. Let's say we connect 3 carbons directly to our carbocation. Remember, that would make this a tertiary carbocation. And let's just focus on each hydrogen connected to these carbons right here. Think about all the chances to hyperconjugate in this case. In this case, you could have either one of these bonds hyperconjugate with that central carbon. And remember, in doing so, we have what's called an electron donating effect. And that is, remember, each electron in the CH bond is able to donate towards the empty p orbital like this. And think about this as well. Each one of those carbons directly connected to the carbocation has 2 other additional hydrogens connected to it. So that gives us even more chances to hyperconjugate. So that's why we observe this trend. It simply means that the tertiary carbocation is the most stable because he has the greater ability to hyperconjugate. So what are our key points here? Well, number 1, we know the trend now. Carbocation stability follows this trend. And 2, we know why. It's hyperconjugation that explains carbocation stability.